Well, it's time to talk a little ozone. It's something that we have in our atmosphere that is critical for life on this planet. In fact, when our Earth, in the early stages of its formation and throughout much of its history, didn't have ozone in the atmosphere, and without that ozone, life could not exist on land. So this one substance, made up of very simply 3 oxygen atoms, is critical for life on our planet. Our purpose today is to look at this substance and then find out what our impact has been on the layer of ozone that surrounds our planet. So let's start with a quick look at our atmosphere. And when you take a look at our atmosphere, just remember that our atmosphere is a very, very thin envelope of air around the Earth. It's not a real thick layer. It's very fragile, and it's something that we can influence. When you look at the atmosphere, we can basically break it down into its 2 lowest layers, which are the 2 most important, and that is the troposphere at the bottom. And the troposphere is where all of our weather occurs. Okay? It's the lowest layer of the atmosphere. It's as you rise up in the troposphere, the temperatures drop. All right? And then you hit a point where the temperatures start to rise as you go up into the atmosphere. And at that point is where the stratosphere begins and the troposphere ends. And we usually give that the name tropopause. Just in case you ever hear me say that. The tropopause is the point at which the temperatures start to rise as you go up, indicating that you are in the stratosphere. Now, it is in the stratosphere where all this ozone is located. All right, so you have the ozone sitting up in what we call stratospheric ozone in that layer. If you do get ozone down in the troposphere, all right, especially at the lowest layers near the surface, it is considered a major photochemical smog pollutant because ozone is an irritant, and it will irritate your eyes, your nose, your throat. Okay, and in high enough concentrations can actually be used as a disinfectant to kill organisms. So you have both those options with ozone at the lowest layers of our atmosphere. All right, so we're worried about stratospheric ozone because that's the important stuff. All right, so it's up here in the stratosphere, above all the clouds, above all the weather, where the sun shines constantly, and the ultraviolet light is very, very intense. And it's that intensity which helps create ozone. So ozone is taking a molecular oxygen up in the stratosphere, along with the diatomic oxygen that we're familiar with down here in the troposphere, and with a little energy of UV light, combines to form an ozone molecule, or O3. Okay, so if we look at it through the whole entire stage, we're looking at the energy from the sun striking the oxygen atom, the diatomic oxygen, breaking it apart, which you see over here. All right, you're going to break it apart and create molecular oxygen up there in the stratosphere. All right, so then that molecular oxygen can then come and combine with another diatomic oxygen down here to form 3 oxygen molecules that we know as ozone. All right, and that's how the process works. Now, what's very interesting about this process is that it's not just a one-way process. This is an equilibrium equation where, give me a second here you can take this concept and do it this way. Molecular oxygen plus diatomic oxygen makes ozone. And then ozone absorbs ultraviolet light when it hits the ozone, and it breaks it apart back into molecular oxygen and diatomic oxygen. So what you have is a 2-way equation in equilibrium with each other. So you've got the process of ozone formation being in complete equilibrium. Right? Very, very important. Keep that in mind. And that equilibrium has been going on in our stratosphere for millions and millions of years. All right. So we now have this ozone above us that protects us. And if you look at the Earth's atmosphere and the thickness of ozone, you could see that the ozone layer is thickest where we need it the most, which is kind of nice. And that would be at the equator. Ozone is measured in a unit called a Dobson unit. All right, so when you see Dobson unit, you're talking about ozone. And if you look in the world map here, you'll see that where the darker reds and purples are, that's where the Dobson units are at their greatest. All right, and this would be an area where you have most intense sunlight around the equator. And then when you get up by the poles, you have almost zero Dobson units, or a very, very small amount, because you're talking about a very low intensity light. Because remember, you need that ultraviolet light, that intense sun, to create the ozone, which is good because where you create it is also where you need it. So the higher the Dobson units, the more ozone you have, the thicker the ozone layer. Okay. So what does the ozone layer actually do? Well, it actually prevents ultraviolet light from reaching the Earth, most of ultraviolet light. And there are three types of ultraviolet light, ultraviolet A, B, and C. And what's great about the ozone is that it completely prevents UVC from getting to us, while it allows most of UVA to get through and also blocks most. Now I'm ready. All right, so we got UVA. Look at that, much better. So UVA has the longest wavelength. All right, UVB is the medium. UVC has the shortest. I'm going to go down here as the shortest. All right, so UVC being the shortest wavelength, therefore it means it's the most powerful, and this one is literally deadly on contact. All right, and what I mean by deadly is that it destroys living cells. So it's very good that the ozone layer keeps UVC from getting down to the Earth. Now, UVA, being the longest wavelength, doesn't penetrate our skin as well, but it is linked to sun exposure, to skin cancer, and the cataracts and the problems caused by too much radiation from the sun. UVB is the one that we are most concerned about because it's a little bit stronger than UVA. All right, it's correlated with increased risk of skin cancer, cataracts, and other eye problems, and also suppresses the immune system. So, luckily, 99% of this is blocked by the ozone layer. Only a small percentage of UVB gets through. Where UVC is blocked completely by the ozone layer, UVB, a small percentage gets through, but we're concerned about that small percentage because of the more higher energy, therefore the more problems that it will cause for us and for life on the Earth. All right? And then UVA pretty much gets through. All right? And we are concerned, but not as concerned. Again, with UVA, we're talking more about just the excess exposure being linked to skin problems and stuff like that. Okay, so the ozone layer blocks all of UVC, most all of UVB, 99%, and none of UVA. All right, important things to keep in mind because when we get into the destruction of the ozone layer, we run into problems here, and that's what these are the problems that we see. They found out that if you reduce the ozone layer, all right, by a small amount, you're going to increase the amount of UV light reaching the Earth, and I think that makes sense. So we'll see that coming up. All right, moving along here. CFCs. Whoops, not that CFC. Nope, wrong CFCs. Man, nope, not that one either. There we go. CFCs. We're talking about chlorofluorocarbons, all right, that are commonly seen in the past in aerosol spray cans and stuff like that. This chemical, this CFC chemical, was created in large quantities in the 1950s and 1960s. It was considered a wonder chemical. It was used extensively for all kinds of things because it was not harmful, it was not flammable, it was non-reactive, all right, and you could use it in a variety of contexts without causing any damage. And not only that, it also was very good at absorbing heat. So it could be used as a refrigerant. Therefore, it is often referred to as Freon, which you might have heard of before. All right, Freon is another name for a chlorofluorocarbon. All right, so we started using these chemicals in mass quantities on the planet, and without ever thinking or taking into consideration what happens to a CFC molecule in the atmosphere. Because a CFC molecule doesn't react with anything, that means that a CFC molecule remains in our atmosphere indefinitely. So Sherwood Rowland, a scientist at UC Berkeley in California, looked at CFCs and tried to figure out what happened to them after they were emitted from a spray can or something. And he found out that CFC molecules can stay in the atmosphere for hundreds of years, and that the CFCs over time, and we're talking a period of anywhere from 10 to 20 years, slowly work their way up into the stratosphere. So that the CFC molecules were actually going upward into the stratosphere where the ozone layer is located. So what was the consequence of that? Well, that took a little bit of work, and they found out some interesting things. Okay, so again, CFCs are found in all kinds of stuff. All right, and so looking at what it did, let's do this. And I apologize for those people who don't like chemistry. Let's give it a chemical analysis here real quick. All right, so what we're going to do is we're going to take a CFC molecule and do something a little bit unique with it. A CFC molecule, say it leaked out of an air conditioner, sits around in the troposphere for 20 years, works its way up into the stratosphere, and when it gets into the stratosphere, it comes in contact with intense UV light, and especially one that's never been in contact with, which would be UVC. All right, whoops, UVC. So what happens is when this UV light comes in contact with a chlorofluorocarbon, it breaks the molecule apart. Now think about it. It's chlorofluorocarbon. You should know the three elements that are in there. Chloro meaning chlorine, fluorine, and carbon. So what happens is when it gets in contact with this intense UV light, it breaks apart into a molecule which isn't that important, but here's the key. A chlorine atom breaks off. Now, why is that important? Well, chlorine now is highly, highly reactive. In the troposphere, if you release chlorine, it would react with something and never make it up into the stratosphere. But once it's in a CFC molecule, it becomes stabilized. And now it has a way of being transported up into the stratosphere, where when the CFC molecule comes in contact with UV light, all right, intense UV light, it breaks apart and the chlorine is released. And here's what happens. The chlorine atom combines with ozone and breaks the ozone molecule apart into a chemical known as chlorine monoxide. And if you balance it, diatomic oxygen. So chlorine monoxide is the smoking gun. If you find chlorine monoxide in the stratosphere, you know ozone has been destroyed. So now we have a chemical way of destroying ozone. But that's not where it stops. Chlorine monoxide, being reactive itself, comes in contact, if you remember the equation as ozone forms, it's molecular oxygen plus diatomic oxygen makes ozone. Well, that chlorine monoxide can come in contact with molecular oxygen up there in the stratosphere, and it forms, ready? Chlorine plus O2. What just happened? You just released the chlorine atom to go back and destroy more ozone. That's the problem. one chlorine atom can destroy up to 100,000 ozone molecules on average. And that's significant because it doesn't take that many CFCs to destroy the ozone layer. The ozone layer itself isn't that thick. And so by putting just a few CFCs up there, it could have large consequences. So chemically, you can see how this process works. That you take and release the CFC into our atmosphere. Because it's stable, it works its way up into the stratosphere, and because it comes in contact with UV light it's not used to in the stratosphere, it becomes unstable, breaks apart, chlorine is released, and chlorine then goes and destroys the ozone. So you can see it right here. You can go through this on your own step by step and you'll see the exact process. All right, and hopefully it'll make sense to you, so feel free to pause this, take a look at that diagram, and understand that. So, CFCs are not the only culprits that can destroy ozone. There are others. What you see on this diagram are some of the other forms that I want to spend just a minute on real quick. CFCs are the one with chlorine in them. CFC 12 being the most commonly used. And CFC 11, okay, and then we have CFC 13. And you can see the length of time they spend in the atmosphere. And here's the thing, many people talked about, if we stop producing CFCs, it's not going to do any good because CFCs remain in the atmosphere for so long, it's going to continue to destroy ozone for a long, long, long time ahead. And that is true, to agree. But that doesn't mean we should not stop making CFCs. You have carbon, like carbon tetrachloride is another one that's used in solvents. And then you have a few others. But if you go down to this one, the halons, now you're talking about a different chemical, bromine, which also destroys ozone. So you find halon in things like fire extinguishers and pesticides. Okay, and you also have a third. So you have chlorine being one, which is found in your air conditioners. It's as a coolant, okay, as a propellant for spray cans and stuff like that. You have bromine, which is found in a chemical called halon, which is usually in fire extinguishers, which, by the way, if you look, lasts in our atmosphere quite a long time. And then you have a third one, which you're familiar with because it's also an anthropogenic greenhouse gas. All right, and mostly your nitrogen oxides, especially this one. All right, which you find in fertilizers and, believe it or not, jet fuel, which is really significant since jets fly in the stratosphere. You literally are taking the chemical, ozone-destroying chemical, directly to the stratosphere. All right, so those are the three. Keep them in mind as you look back over this and try to understand all the chemical processes that are destroying the ozone layer.